Okay, thank you so much, Dirk. I am Martin Bluschke, a postdoc at the UBC's Quantum Matter Institute, and today I'm going to talk about the non-equilibrium dynamics of C4 rotational symmetry breaking in the superconducting compound LESCO. So first I'd like to acknowledge my collaborators, especially Andrea Damascelli, my supervisor at UBC, and Dave Hawthorne, who instigated this project and has co-supervised it, as well as his PhD student, also at University of Waterloo, Naman Gupta, who has collaborated with me from the very beginning on this project. Also, especially, I'd like to acknowledge Hoyoung Zhang, who is responsible for developing the equipment at the Pohang Accelerator Laboratory that we used for this experiment. And we also have collaborators at PostTech and at the SLAC National Laboratory. So I'm going to talk first a little bit about rotational symmetry breaking in the CDW state of the cuprates, and then talk about signatures and resident X-ray scattering of CDW-driven rotational symmetry breaking. Okay, and finally, the results of our pump probe time-resolved resonant X-ray scattering measurements from the europium-doped LFCO compound. Okay, so without getting into detail, I'm going to say the charge density wave in the cuprates is maybe already self-motivated. Here I want to draw your attention to the fact that it's typically associated with the breaking of the lattice translational symmetry. So we're typically looking at diffraction at sort of a finite Q in the plane. But it's also often, but not always, associated with the breaking of rotational symmetry with respect to the C4 rotational symmetry of the copper O2 plane. Okay, and in this talk, we're going to loosely refer to this concept as nematicity. So nematicity is often more rigorously thought of as the rotational symmetry breaking without the translational symmetry breaking. But here I want to focus on these two symmetry breakings and how they can happen together or independently of one another. Okay, so just to give you a picture of the type of thing I'm talking about, you can have the symmetry of a lattice, a square planar lattice. You can break translational symmetry in some sort of charge order without breaking rotational symmetry. You can break both rotational and translational symmetry in a stripe-ordered state. And if you introduce enough dislocations and phase slips in this stripe-ordered state, you can achieve a state which has broken rotational symmetry without explicitly breaking the translational symmetry in a long-range way. Okay, so charge density wave in the cuprates, how does it fit into that sort of characterization? Well, we have a number of different examples. So typically, the CDW in the cuprates is this rotational symmetry breaking is being pinned to disorders or to some sort of structural distortions. So in the case of the 3D CDW, which you see in high fields or uniaxial strain in the cuprates, the uniaxial character is pinned to the orthorhombic B direction. Okay, it's just the lattice symmetry. In the case of the 2D CDW, the one you see in ambient conditions, in YBCO, but also the bismuth-based and mercury-based cuprates, we see uniaxial CDW domains along both the A and B directions, okay? And it can actually be quite complex to, in a scattering experiment, extract or sort of, elucidate this uniaxial character. So Bernhard Keimer told us yesterday about these complex strain experiments where you're able to really, get at this uniaxial character, but it's not always trivial. And in fact, there's been recent measurements by Alex and Eduardo, which have shown us actually that you can see charge density wave correlations at all directions, and Fabio, of course, in the copper-oxygen planes, actually showing us a heightening of the symmetry of the charge order with respect to the lattice. Now, of course, we don't know what the microscopic arrangement of those fluctuating CDWs are, but the point is it is fundamentally interesting to independently probe rotational and translational symmetry breaking in this state, okay? So our focus will be the 2 and 4 cuprates. Here you have this special phenomena that there's this low temperature tetragonal distortion, okay? And this is a structural distortion which is uniaxial in the copper-oxygen planes, but this uniaxial character alternates from one plane to the next, okay? And this can be taken advantage of because it basically gives you a periodicity along the out-of-plane direction, okay? A periodicity associated with this uniaxial character, right? So in diffraction, now we have two features we can look at. If we look at the in-plane momentum transfer, we can have finite in-plane momentum transfer showing us the translational symmetry breaking, or we can go to Q equals 0 in plane, where we're seeing essentially this rotational symmetry breaking, and we're able to see it because it's periodic in the L direction, okay? So this doesn't have to be translational symmetry breaking in the plane. You can just have nematic character. As long as it's rotating 90 degrees each time, you'll get a Bragg peak there, okay? Because the copper, if you go to the copper L3 edge, the low energy, states are now anisotropic, and that anisotropy is rotating as you go up, okay? And the same is true if you go to the oxygen And now, the particularly interesting thing here is that this reflection is going to have now components which are both induced by the structural anisotropy, so purely associated with the anisotropy coming from the LTT distortion, but you'll also have additional anisotropy or additional rotational symmetry breaking or nematicity associated with the CDW itself, okay? So an electronic and a structural component. And we're going to try to pull those apart by using the spectroscopic contrast you get in resonant X-ray scattering. So we're going to look at, for example, the apical oxygens, which should be purely associated with the structure, and then compare that with signals we see using the copper L3 resonance or the planar oxygen K resonance, which have additional sensitivity to the copper oxygen planes. Okay, so here we go. First, just in equilibrium to show you how this looks, we choose as our study candidate LESCO, and the reason we do this is because the LTT distortion is strongly separated in temperature from the charge order. Okay, so if we now go to this 001 peak, which shows us this rotational symmetry breaking, at the apical oxygen, we can see just an onset at the LTT temperature, 130, okay, and an order parameter like onset. If we go to the copper L3 edge, then we see the same thing, so rotational symmetry breaking associated with the LTT distortion, and then a lower temperature associated with the onset or correlated with the onset of translational symmetry breaking in the CDW phase. We get additional intensity coming up in this 001 peak associated with the rotational symmetry breaking. So that says we have now a resonant X-ray scattering signature, this red one at the copper edge, which has two components, an electronic component associated with the rotational symmetry breaking driven by the CDW, or the nematicity driven by the CDW, and a component down here which is associated with the structural anisotropy, okay? Now, if you have really these two different components, and one is electronic and one is structural, they just have vastly different responses in the time domain. So we say, let's just go and do a naive pump probe experiment using a 1.55 eV laser and see how do these, can we dissect or, let's say, pull apart these two different components. We have resonances, we have temperatures, and now we're going to have our time domain to separate them, okay? So we did this by going to the Pohang Accelerator Laboratories resonant soft X-ray scattering instrument. And without getting into the details, I'm going to say that this is a very user-friendly instrument developed by Hoyoung Jang. He's done great work. We're working with a 1.5 eV pump laser. We're using 60 hertz rep rate, soft X-rays, and our overall time resolution was on the order of 100 femtoseconds. So this is sort of the geometry of the experiment. And this is what the signal looks like. So the first thing to notice is that compared to the CDW reflection, this thing is much more intense. So it allows us a lot more sensitivity, let's say. And this is just to show you what the order of magnitude of the signal is that we are looking at. So here, the dotted line that you can hardly see is the equilibrium 001 peak. The red curve is sort of the maximum suppression in a fluence regime, which is the one we're going to operate in, so around 50 microjoule centimeters. And then the blue curve, which looks sort of the same as the laser off curve, is after 20 picoseconds, so it's almost fully recovered. Okay, so the first thing that we want to do is we want to establish what are the dynamics of the structure, okay? So the way we're going to do this again is we're going to start by studying at the apical oxygen K resonance, where we know that we're just seeing, the effect of the LTT distortion on the lanthanum oxide layer. And we do time delay curves as a function of fluence, okay? So at high fluences, you can see that, over a couple of picoseconds, this hot quasi-particle population that you excite with the pump couples via electron-photon coupling to the lattice, and you start to get a suppression of the LTT peak, which doesn't recover for maybe hundreds of picoseconds, okay? It's something.
Question.
Yeah.
Pump probe mismatched? Or?
Not strongly because of the soft X-ray regime, yeah.
I see. So this is
should be on the order of, I guess, 100 nanometers.
This is a true change.
This is a true change, yeah.
Meaning that it shouldn't get larger because of the...
No, that's right, yeah. Oh, I'm jumping ahead. So then I want to say, okay, so now let's reduce the fluence. And if we get down below 100 microjoule centimeters, we get into a regime in which the lattice is essentially unperturbed. Okay, we don't see a strong perturbation of the lattice. So we say that's now where we're going to work. Now we're going to go to the copper L3 resonance, or the planar oxygen K resonance, where we have sensitivity to the low energy physics of the copper O2 planes. And hopefully then we'll still be able to perturb the electronic degrees of freedom with this low fluence and know that we're exclusively touching those electronic degrees of freedom. And so that's what we do. And here you can see, as a sort of control case, is the apical oxygen resonance. Again, no effect at this low fluence. This is the laser on divided by the laser off, okay? As a function of temperature. You go to the copper L3 edge, and you get this temperature-dependent, fast response that looks exactly like the CDW dynamics in LBCO, measured by Matteo Mitrano and others. And here you can see the temperature. It goes exactly with the CDW. So we're kind of just measuring the CDW. but we're measuring the rotational symmetry breaking in that state directly, okay? And now you can also ask, well, this is about, the copper L3 edge, that's 930 eV. It's, almost 400 eV away from the apical, from the oxygen resonance. Maybe there's something more complicated going on. So then we say, well, okay, then we're going to go and test that by moving to the planar oxygen, which is only, that resonance is, so this is the oxygen K edge, and you have a feature here associated with the planar oxygens, and then at higher energies, the one with apical. We move between the two, and what we find is, at the planar oxygen K resonance, you have a behavior which, mirrors what happens at the copper L3 edge. So this gives us strong confidence that, here we're looking essentially at the physics of the copper O2 plane. And the other thing that I want to point out is that the recovery time scale, which is similar to what is seen in the CDW, is also sort of the same as what we see as the suppression time scale of the lattice. So in my mind, that's, naively, I'm going to say, okay, we're exciting, we're heating up, exciting all these hot quasi-particles, which, are coming out of the CDW phase. And as they couple to the lattice and heat up the lattice, destroying the LTT, they then condense back into their CDW, okay? This is sort of my naive picture. And what do we do then? Well, okay, so then we try to study the fluence dependence of this thing. So we sit here at the time delay of maximum suppression. And, since we have a very strong signal, we're able to really, collect this data in a very modest amount of time. We now do a fluence scan here, and we see if you go at the apical oxygen associated with the structure, you see a very sort of weak linear response in the whole fluence regime that we have. This is telling us, yeah, we're in a linear response regime. The lattice is just getting more and more perturbed, but only slightly as we increase the fluence. If we go to the planar oxygen resonance at high temperatures above the CDW phase, we have the same sort of response. But if you cool down into the CDW phase, this upper curve here, then you see there's this fast saturating response at low fluences, and then something that looks more like the structure at high fluences, okay? So this here is, this is sort of like 0 means no pump probe effect, and 1 would be a full suppression of the peak. Okay, that's this type of, that's what I'm plotting here. So then we just naively call this thing our background, okay? Fit it with a line and subtract it from all of our low temperature measurements. We have a bunch of them, and that's what I'm plotting here. And this is what I'm going to call the sort of suppression of the electronic nematicity, or the suppression of the rotational symmetry breaking as a function of fluence. And the only thing that I want to point out here is, if this effect were maybe a pure thermal effect associated with, transient electronic temperatures, you might expect that actually the saturation fluence would shift to lower fluences for higher temperatures. So maybe this is evidence that we're, this is not a purely, that we're somehow in a non-thermal regime when we're doing this experiment. But that's maybe there's something more behind that. 1245. So I'll show you my conclusions. CDW, as we kind of already know, in 214 compounds comprises a significant rotational symmetry breaking component. But now, we show that we can explicitly probe that, and in particular probe the dynamics of both the translational and the rotational symmetry breaking separately. The lattice dynamics are typical of sort of a slow coupling to the phonon bath. The nematic order is suppressed much more quickly, showing that it's directly coupling, a direct coupling between the excited quasi-particle population and that nematic state. And then the recovery of that electronic nematicity goes over a time scale similar to the suppression of the LTT. And we have these two different sort of fluence dependencies, which can also be used to separate the two. The only sort of final comments I'd make, a bit of sort of advertisement. One, sort of in a parallel session right now, my co-author Naman is presenting a similar work where he's done an equilibrium study of the same compound, sorry, not of the same compound, the same signal, but in the neodymium-doped LSCO. And there he tries to track this nematic character into a doping regime in which CDW doesn't exist, and is interested in sort of exposing a purely nematic region of the phase diagram, which could be then interesting to, in a time-resolved study, compare with what we've looked at. And the sort of other direction that we're interested in going. So actually just today, a paper together with Alex Fagno was being published where we used coherent light to study the mesoscopic texture of antiferromagnetic domains in a completely different material. And I think there's maybe some future direction for doing stuff like this here as well. So basically our experiment is opening up a time-resolved study of nematicity with a very strong signal where you could maybe even hope to see some sort of coherent effects as well at an FEL later with the 2D detector. But that's dreaming and thunders. Thank you very much.
Thank you very much, Martin, for this very clear talk. Nice results. Questions? Yes, Matteo.
Martin, thank you for the very nice talk. I think I've been missing. I would like to go back to the timescales.
Yeah.
So at some point, you showed that the 001 becomes, has a slow dynamics, and then you change energy, and the copper ledge goes faster, recovers faster because you're tracking the CDW. So why there is this difference between in timescales?
Sorry, you mean the difference between this leading edge? So I see there's two time scales always, right? There's the suppression and the recovery, right?
Recovery. So what about the recovery? So here you're measuring the same peak at two different energies, and in one case it's recovering very slowly, in the other case it's recovering faster.
Yeah. Well, so again, I would say this is what I would call typical of the structural response. So you have this suppression which is slow, like the electron phonon, and the recovery is happening over this time scale where the phonons are exiting the beam spot. It's something that's much longer. That's how I'm understanding it. So you've now excited all these lattice vibrations. Now they have to sort of diffuse.
But do I understand correctly that you're measuring the same peak, and the same peak at different energies recovers with different time scales?
No, but it doesn't. So that's the thing. So now here's the trick. So if I now go to here and I pump at a high fluence, one comparable to this, then I will also get overset on this electronic signal a lattice type signal which doesn't recover and looks exactly the same. I'll get the superposition of the two. But at low fluences, there is no lattice signal, and so I'm superimposing at the copper edge, no signal with just this electronic response. Does that answer the question? You have to remember that these measurements here are much higher fluences. These are at one.
I will ask you later because in LBCO we see something different.
Okay. Yeah. Maybe I didn't understand the question. Let's talk about more.
Okay. More questions? Can I ask a quick one? Because you mentioned at some point these quasiparticles will then recombine into the charge density wave somehow, or
it's a picture. I don't know. Trying to understand it.
So could you extract some time range or time constant for that effect?
Well, wouldn't that be this one then? So if we try to fit this naively, we get something on the order of 1
But then
picoseconds.
strongly fluence dependent. Yeah. Okay. Somehow.
No. This is the time. This is.
Okay.
So the peak has gone back to its full intensity.
Okay. You say after 5 picoseconds they are all back somehow.
Yeah. How you want to? If you do a 1/e, it's just 2 or 3 picoseconds, but.
Okay. More questions? No? Okay, so then let's thank the speaker again. Thanks, Martin. So we have one